All right, guys, today we got the least squares regression line. I'm trying to do, I've moved my office outside because it's too pretty. I live close to the airport. You may hear airplanes. I know there's a mower going. Somebody's blowing leaves. No telling what you're going to hear. If the sound quality is too bad, I'll go back and do it again. But I'm going to try it out here, and I'll show you why on the next slide. Least squares regression line. Least squares is a new name for what we've been doing the whole time. The regression line on our calculator is the least squares regression line, which is very nice for us. So not a whole lot new today, but a little bit, so really pay attention. There's not a whole lot of examples on this video, just a lot of information, so make sure you get that. The biggest piece of information, tomorrow on Wednesday, we have our first Google Meets. E period, 1:30, be there, or B square, be there, 1:30, you'd have to be there. F period, 2:15 on Wednesday, right after E period's over, 2:15 on Wednesday, and I got to give you some information there, really important that you're there. Of course, attendance will be taken. Need to see your face anyway, since it's always been about 5 years, so that's Wednesday. Okay, least squares regression line. This is why, before I get there, this is why I'm outside from my, there goes a car down the road, from my front porch. That's what I see, so that's a lot better look at my walls and inside the house, so that's why I'm out here today, and will be a lot of days probably. Okay, regression line. A regression line is what we've been doing, to be honest with you, but new name, and you'll see why, is a straight line that describes how response variable y changes as an explanatory variable x changes. So the regression line is going to tell you how y changes as x changes. We often use a regression line to predict the value of y for a given x, which we've already done that a little bit. Regression, unlike correlation, requires we have an explanatory and response variable, and that was in yesterday's lesson. I'll show you a picture of one down here. There's a regression line drawn through a scatter plot. That's the least squares regression line. And I'm going to show you in the next slide why it's called the least squares regression line. All right. When we draw our line, I picked 3 points from that last picture and kind of blew them up real big for you. The line is our prediction line. That's our least squares regression line. We've got a prediction line. We've got a regression line. LinReg, you know, everything we've called it, line of best fit. The official name is least squares regression line. When we draw that, there's always error. So like these points you see, like right there's a point, those are the real points. Those are actually the observed points. The line serves as a prediction, and obviously there's going to be error involved because our prediction is going to be not going to be exactly what the points are. That error you can find by doing the observed value minus predicted value. Those are called residuals, by the way, and that's going to be what the next lesson is about, is residuals. Residuals, what's left over in between here? What's the gap between the observed and the predicted? That's called the residual. So what we do to get the best line possible is we try to have our residuals be as small as possible to that line. We want our residuals to be very small. But there's so many of them, what we do is we add up the residuals. We take the sum of them, we add them up to see how well we did. We take all the residuals, just add them up. But the problem is some points are above the line, some points are below the line. And so what happens is some of our residuals end up being negative and some end up being positive because of the way we subtract. So what we do after we subtract is we square them. Okay, so we find our differences we find our error, our residual, we square it to make them all positive, then we add them up. And so what we want to find the line is where our least amount of squares values are. In other words, what is the least squares regression line? I hope that makes sense. That's the best I can do to explain it. I may try another video next couple of days, but that's why it's called the least squares regression line, is because the residuals are as small as we can possibly make them when we square the residuals to make them all positive so we can do the math with them. All right, least square, and here it is written out. Least squares regression line, the line that makes the sum of the squares of the vertical distances of the data points from the line as small as possible. So we're taking each of the data points, going the vertical line, find the distance, square them, add them up, and we want that line to be the line of best fit, or the least square regression line is the line where the sum of the squares is the smallest. And there's only one line where that is true, where the sum of the squares is the smallest. Facts about the lines. Number 1, it looks at the distances of the data points from the line only in the y direction. Notice we We didn't worry about going horizontal, we just did vertical. Everything's about the y. X and y play different roles. When we did correlation, I told you you can do X and Y, don't matter which one's which, doesn't matter which one's L1, which one's L2. When you're doing regression, it does matter because y varies as X varies. So your y you got to be careful what you're using for your y. Number two, this is huge. This is one of the most important things today. The square of r squared, is the fraction of the variation in the values of y that is explained by the linear correlation or linear relationship of y on x. That sounds really complicated. I'm going to show you one on the next slide to kind of help that make sense. At least I hope it makes sense after you see the next slide. But get that down. R squared, the fraction of the variation in the value of y that is explained by the linear correlation or relationship of y on x. Because part of the change in y is going to be because, there's linear relationship, so as x changes, y changes. That's going to be part of the reason the y changes, but may not be the only reason. So it's a fraction of the reason. Okay, let me show you one. I hope this, make sure you get this slide. If you have to go back and watch this again, this is so important and so huge. I hear an airplane coming, so just prepare yourself. Okay, this is an example I showed you the other day. This has shoe print length down here, person's height going this way. Do the least squares regression line on there. Notice I said that's the best line there is because the residuals are small as they can possibly be. It tells you what R is right here. R is 0.813, which is a good R. There's definitely a linear relationship. So what you do is you take the R and you square it. So I took that 0.813, squared it, got 0.661. And here's what we can conclude. We conclude that 0.661 or 66.1% of the change in the height can be explained by the change in the shoe print lengths. All right, so 66% of the change in y is due to the change in x. Now, that's a pretty good percentage, but that still leaves 34%. That means 34% of the change in y can't be explained by lengths of shoe prints, which means there are other variables involved that have to do with height other than just shoe size or what print your shoe makes. It's a big determining factor, but not the complete determining factor. So what R squared tells us is what percent or what fraction of the change in y can be explained by the fact that x is changing. The bigger the shoe, the bigger the taller the person. 66% of that change in the height is due to the change in their feet size or the shoe print. So I hope that makes some sense to you. 34% can't be explained that way, which means there's other stuff going on that explains height besides just shoe size. Imagine that. All right, bottom line. This is the summary right here. A predicted value of y will not necessarily be the exact result that occurs because in addition to x, there are other factors affecting y, such as random variation and other characteristics not included in the study. Way back when we first started stats this year, we talked about something called lurking variables. Variables that just kind of lurk around that create differences that aren't even involved in the study. They're studying something, did a good survey, but there's other lurking variables involved that we didn't take into account. So this is kind of an unusual video in the fact that there's just, it's a lot of information, not a lot of examples. I'm only giving you 2 problems as a Google Doc for homework. Shouldn't take that long. Please contact me. Oh my gosh, I'd love to help you. That's all I'm doing. I'm sitting here making videos, making your assignments, and waiting for you to text me for help. And a lot of people are doing that, which I appreciate. So text or email or whatever, and I will be glad to help you. Don't forget Google Meets on Wednesday. I'll send out a reminder and also an email, and it's also on Google Classroom. Your link will be on Google Classroom because I haven't figured out how to put it on the website yet, so it'll be on Google Classroom. So look for the link to our Google Meets there, and I expect to see everybody there with smiling faces. I will see you tomorrow. Work on your assignment. Good luck. Contact me if you need help. Adios.